Good afternoon everyone, my name is Fajr Al-Failakawi and I am presenting this project together with my teammates Dan Al-Hamar, Mariam Rehani, Noor Hashim and Rahaf Al-Kreibani. Our project focuses on designing an environmentally friendly powertrain for public transportation buses in Kuwait. Currently, most public buses in Kuwait rely on diesel engines, which lead to high emissions and environmental impact. So, our project aims to explore cleaner alternatives by comparing internal combustion engine vehicles, electric vehicles, and fuel cell vehicles. Our goal is to reduce carbon dioxide emissions, meet the target daily range, and still meet the required performance for public transport.
Now I will continue with the company visit. A site visit was made to the city bus company to obtain information for the project, where the team was introduced to their operations, bus models, and specifications. Now I will continue. Internal combustion engine buses are widely used in Kuwait's public transportation system, creating a need for cleaner and more sustainable alternatives. This project focuses on designing an environmentally friendly bus operating from Route 30 from Fahahil to Kuwait City, covering approximately 40 kilometers. This meets key requirements including a range of 400 to 480 kilometers and the bus is designed to carry around 60 to 65 passengers.
Hello, I'm Noor and I will be discussing the methodology part of this project. First, we have a literature review and it was done on ICE and EV and FCV vehicles. Then the vehicle requirements were the range, speed, and the load. We defined them based on real bus conditions. And after that, a MATLAB Simulink longitudinal model was developed to simulate performance. And finally, the system was compared and we selected an optimal design based on those requirements. For this part, real driving data was collected using MATLAB Mobile from a bus route in Kuwait from Fahahil to Kuwait City. This route was about 40 kilometers and it took around 75 minutes and the maximum speed was 85 kilometers per hour. This data was used to create a realistic driving cycle with frequent stops, making the simulation more accurate.
Hello, I'm Rahaf Al-Kreibani. I'm gonna talk about the consumption design. We have showed the consumption design of three types of vehicle: ICV, EV, and FCV. The IC vehicles use a fuel and has a long range, but it produces high emissions. The electrical vehicle uses a battery and a motor, so it's clean and quiet, but it needs charging time. The fuel cell vehicle uses hydrogen to produce electricity. It has low emissions and fast refilling, but it's more expensive. We have to explain the force acting the vehicle. There are three main resistance: aerodynamic resistance, rolling resistance, and ground resistance. We have also calculated the attractive force needed to move the vehicle. By using Newton's second law, we combined all these forces to find acceleration for the vehicle. For the rolling resistance force equation, it depends on the vehicle mass, gravity, road conditions, and the road angle. For the attractive force equation, it depends on the engine torque, gear ratio, system efficiency, and the Y radius. We showed the MATLAB Simulink model used in our project. This model simulates the vehicle behavior, including speed, acceleration, and position. It also includes engine or motor power, road load, and difference resistance. This helps us to analyze and compare the performance of different vehicle types.
I am Dan Al-Hamar. I'm gonna explain the vehicle model simulation. Let me start with the first one. This simulation represents an internal combustion engine vehicles using a longitudinal model applied on the sensor. A gear mechanism with lookup table is implemented where upshift a fuel map is used to compute both instantaneous and cumulative fuel consumption, which is then converted into carbon dioxide by multiplying the fuel volume in 2.68. Electrical vehicle model is simpler compared to the internal combustion vehicle model. So basically we have same longitudinal vehicle model, driver model, and tractive force structure. State of charge is edited compared to the internal combustion vehicle. When we are using the battery, 95% efficiency is considered, but when we are charging the battery, due to the regenerative braking, 90% efficiency is considered. Instantaneous power is calculated. AC load is added when it is integrated for the whole cycle. The amount of energy used is calculated here, and the state of charge is calculated afterward. In this model, hydrogen is used as a primary energy source. The fuel cell converts hydrogen into electricity, which then powers the electric motor. Road load calculation and tractive force are the same for the EV, same 95% depleting efficiency and 90% regenerative efficiency is used. As the fuel cell vehicle has small battery, state of charge of the battery is calculated in a similar way with respect to the electric vehicle model. State of charge of the battery is initially set as 80% throughout the cycle. Using PID controller, we try to keep the state of charge constant at 80%. So now let's discuss the results. The first one is ICE model. Engine power is 315 kilowatts. It is diesel engine with AC load 25 kilowatt hour. Fuel tank volume 200 liter. Gear upshift threshold is considered 1750 rpm. You can see the vehicle speed, gear, engine speed, and output torque in the first graph, while the second graph represents instantaneous fuel consumption, cumulative fuel consumption, and cumulative carbon dioxide. Okay, now let's discuss the results of the electric vehicle model. From the vehicle mass of the ICE, 1000 kg is reduced and the battery weight is added to obtain the vehicle mass. AC load of 25 kWh is used, and electric motor with similar power with respect to the diesel engine is used. Approximately same distance travel according to the simulation. Energy consumed is 65 kWh and battery capacity 783 kWh. For cumulative carbon dioxide emission, every kilowatt energy generation in Kuwait, approximately 0.64 of CO2 is calculated. So for 65 kilowatt hour, approximately 41 kilogram carbon dioxide. Lastly, the fuel cell vehicle results. The vehicle mass is based on the ICE model after subtracting approximately 1000 kg to account the removable of the engine and transmission. Then adding the weight of the battery and hydrogen system. A battery of 25 kilowatts with approximate weight of 150 kg is included, along with hydrogen storage system, weighing about 950 kg, resulting in a total mass around 1100 kg added to the diesel plus platform without the engine. The PID controller operates effectively within this setup, and the state of charge exceeds 80% due to regenerative charging. In terms of emission, hydrogen usage is evaluated based on current production method, where generating 1 kilogram of hydrogen leads to 8.557 kilogram of carbon dioxide. Therefore, consuming 3.57 kilogram of hydrogen, resulting in approximately 30.56 kilogram of carbon dioxide.
In comparison, internal combustion engine and electric vehicles and fuel cell vehicles were evaluated, and EV got the highest range and higher weight, and fuel cell provides similar range with lower emissions and faster refueling. And internal combustion vehicles has the highest CO2 emissions. Therefore, fuel cell vehicle offers best overall balance.
To conclude, in this project we analyzed the current public transportation system in Kuwait and identified the need for a more sustainable solution. We compared different powertrain technologies and developed simulation models using MATLAB Simulink to evaluate their performance in terms of range, fuel consumption, and carbon dioxide emissions. Based on our results, electric vehicles reduced CO2 emissions by 32% compared to conventional diesel buses, while fuel cell vehicles achieve an even higher reduction of 50%. This clearly shows that both EV and FCV are much cleaner alternatives than ICE, with fuel cell vehicles providing the best environmental performance. For future work, further optimization and real-world implementation can be explored to support the shift toward greener public transport. Thank you for listening.